use, right? So the technology has to be designed based on this. So I will just move on comparing some of these technologies. Just give me a minute. I'll just presentation mode. Give me a minute. Pointer. Let me. Yeah. Right. Now let's do a comparison of some of these technologies, right? So we just saw, based on the previous Gartner report, that these are the few key technologies which are dominant, right? So Sigfox LoRa are proprietary technologies using the free spectrum, while similar technologies work on the licensed spectrum, right? So I'll just try to put some of these aspects of these technologies and try to do a comparison. You can get into the details, go through this. We'll be sharing this deck also later, so you can get it through. But few things I want to say, like, scalability, the number of devices perspective, you can see other than LoRa, all other technologies are good. Reliability perspective, cellular is better. Power consumption, maybe EMTC is not good, other ones are okay. Latency perspective, NB-IoT can provide it doesn't provide any low latency, but at least it can provide a guaranteed latency. Coverage looks similar. Mobility perspective, only MTC provides handovers, while Sigfox being an operator, they can provide, try to provide, and roaming across geographies. The way Sigfox work is that they don't, they act as an operator providing the services. You cannot really buy Sigfox network, or there are no separate operators who deploy that. They themselves deploy the services, operators, and use take from them. While LoRa provides more like a franchisees who can set up LoRa networks. So we have seen roaming, mobility, data rates. The Sigfox is very, very low. So basically, it could be used for technologies, the sensor use cases where you need very small data. And that's the reason the power consumption is also pretty low. But this is highly unreliable, very small data once in a while. So those are the use cases good. But I would say that the cellular technology gives a much better, data rate. Even cellular gives a good penetration, or because it implements repetitions. And we'll see what is this repetitions sort of. Yeah, Sigfox is not so secure. Sigfox cost, model cost is pretty low if you compare with other technologies, and cellular is pretty high. And that's the reason why my session focuses on how to design an NB-IoT device SOC, which could meet very low cost, less than $5 and something. Because even though I put it $5 here, if you look at some of the SOCs from a tier one vendors currently, it is, I would say that $15, $20. It's pretty expensive. But then definitely you can have some 5 and very close to these ranges. Yeah. So that would be one of the focus that we would be doing. So that's all on a comparison of these LPWAN technologies. Now we will move on to cellular technology perspective, right? To understand what are the cellular technologies and a comparison of the cellular technologies. Yeah. So. So maybe before we get into the technologies of cellular, let's look at what is the let's look at 5G, and let's look at 5G's roadmap and look at how these technologies are getting in line with 5G, right? Now, as all of you would have seen these diagrams, the KPI metrics and the usage scenarios from ITU many times, all right? But still, I want to start from here. This lighter part is the LTE, while this darker green is the 5G KPIs defined by ITU. Now, none of the devices or the one single network cannot meet all these KPIs, right? When you look at the usage scenarios, ITU has defined this. One is as a enhanced broadband, which is a 4G plus. Then the massive IoT, so that's where the NB-IoT MTC falls down. So we'll focus into this area. Other area is ultra reliable and low latency. Now under that, again, you will see maybe V2X is one of the focused use case, and standards are there clearly for V2X. And there is another category which is coming up strongly now is for the industry automation perspective, which is called NR-Lite. We will spend some time on NR-Lite, which is not a massive IoT. It is a critical IoT, industrial IoT use case. But then, our focus will be on this part as well as on this part. Okay? Now, coming on to the NB-IoT and EMTC, these technologies are this slide, what you see here, it started in 2016 as part of release 13 of the 3GPP specifications, right? Then it had two more releases, 14 and 15, as part of release 16, which is planned for this year, this month, later this month. This technology gets into the 5G standard. So for the 5G, rather than defining a new standard for the massive IoT, they are going to continue to use NB-IoT EMTC. So you can just see how LTEM, the EMTC is also called as LTEM. I might be using this term interchangeably. So LTEM and NB-IoT, you could see that how currently working this as the LTE spectrum. But the same thing will continue to work into the 5G NF spectrum because in the 5G, you have the forward compatibility for the 5G numerology, which allows you to take new technologies, new numerologies, new things to be defined within that. If you have seen the 5G numerology, there are specific areas for URLCC, EMBB, and there are some areas which is kept aside. So these two technologies can directly get into the 5G NR. So that's how it becomes the new technology for 5G. Yeah. Now, one more slide I want to show here, the commitment by the operators for this technology, because I can talk technology, but then the question will be that, okay, yes, there's a technology, but is it something adopted by operators? What is the things happening there, right? So this is a report from GSMA, which shows currently the number of operators who was deployed in NB-IoT and LTEM, and both NB-IoT and LTEM. You can see mostly the Asia is mostly to do with the NB-IoT is a focus area. Slowly they want to deploy LTEM as a later stage. While if you look at that is mostly part of Europe also went with the same approach. But if you look at the US, they went with the LTEM first, then they added on NB-IoT. So if you look at this way, there are hardly any operators who are really focusing only on LTEM. So it is more of NB-IoT or NB-IoT plus LTEM. So there are 129 operators who are already deployed, and in India, I think definitely all the three main operators have proposed for has plans for NB-IoT. I don't want to comment on one specific operator because all of them have plans, and some of them are already in the trials, and soon they'll be deployed. Now, starting some commercial services. And one more slide to add on to this is Eric's Mobility Report 2019. So you could see this shows a comparison about the IoT connectivity projections for the future, where you could see that the lighter part, which is 2G, 3G connectivity, now 2020, it's going to be flat. It's not going to be major increase. And also the darker part, if you see, there's no major growth seen on the 4G, 5G broadband IoT perspective. Some of the increases coming from the critical IoT, but otherwise the current IoT connectivity by 2G, 3G, 4G is going to be stagnant, while you can see, a huge increase projected for the NB-IoT CATM deployments. So this is going to be a big opportunity. Many of the reports projected very high CAGR and business cases for that. I'm not getting to that more. We'll get into the technology. Just wanted to give a feel that this is projected to have a good roadmap going forward. Yeah. Yeah. So I just want to start a technological comparison of the three technologies, because I told three technologies at the beginning, later focused on the two. So when 3GPP started these technologies in 2016, they different three technologies. One for ECGSM, rather it is a GPR, as though it's called ECGSM. It's a pure data connectivity. And NB-IoT was completely new. EMTC or LTM is the lighter version of LTE. So I just put release 8 LTE CAT3 as a reference to show the parameters, how these technologies are doing with respect to CAT3, which is a baseline. For example, if you take EMTC or NB-IoT, the base version of 3GPP is release 8. This is from there it has diverted for EMTC and NB-IoT. Right? So you can, this is only for comparison. This is not an IoT connectivity. Now, this is just showing mainly the main purpose of this to show how the complexity of the modem comes down from CAT3 is an LTE to NB-IoT. You can see a huge, complexity reduction. So the technology was defined. You can see the data rate comes down for both uplink and downlink. And you can, one interesting thing normally you can see, normally any technology, the downlink data rate is more. But for NB-IoT and EMTC, the uplink is more because these are IoT use cases where the sensors are expected to send data, not the downlink. So uplink is the priority here. So you can see this, compared to this, right? So duplex mode perspective, these systems are half duplex, which means only downlink or uplink at any time. Maybe EMTC has the option of a full duplex too, because EMTC supports voice. While ECGSM and NB-IoT does not support voice services, it supports only data services. So because of the duplex part, the number of antennas has come down one, and the bandwidth, and yeah, you could see that there is an increase in the ECGSM for the extended coverage perspective. Now 33 dBm, it is increased, but NB-IoT can achieve the same coverage or a better performance with the 23 dBm. So that is a different, one of the differentiated thing or good thing about NB-IoT. Right? Now you could see that normally the receive coupling loss, which defines the cell boundary, right? Normally it's defined as 144 dB. But in case of Cinder, you could see it as you could afford more coupling loss. Now we'll see how the retransmissions etc. helps the technology to achieve this, right? And from a battery perspective, the power save mode and EDRX as the two features were introduced for all the technologies, where a power save mode is a device where the device tells the network saying that I'm going to sleep, don't disturb me. We'll get into that also later. We have seen the extended coverage, how the increase in the coupling loss helps in the extended coverage. So basically what we are trying to see is that we have the technological definition has brought down the complexity of the modem, but at the same time it provides extended coverage, it provides low battery. So we are just trying to meet the LPWAN requirements which we have seen at the beginning. Yeah. So this is a slide just to show how the performance of this, these three technologies between them, as well as comparing with the expectations, right? If you see here, you can see that the 4 deployment scenarios being compared here. One is ECGSM, other is NB-IoT as a standalone, and NB-IoT is in band. See, NB-IoT can be deployed as a standalone, because it's a 200 kilohertz. It could be on a so very similar to the GSM channels. You can reform that and use it, or it could be deployed on the guardbands of the LTE carriers, because the 200 kilohertz exactly fits in there. Also, 200 kilohertz is the carrier frequency, subcarrier frequency of LTE. So you could use a in-band in LTE deployment for NB-IoT. So now we'll see from the data rate perspective how these three technologies perform very near to the cell base station and the middle of the cell, as well as the cell boundary. So the 155 dB coupling loss is considered as a cell boundary. In case of IoT perspective, otherwise normally in LTE, this is the cell boundary. So this already extended. While here, this is an extended cell boundary, which is 164 dB. This is a minimum, or the maximum coupling loss that could be used. Right? So you could see that NB-IoT here as a standalone deployment. All right, it could, it gives a very good performance at even at a 164 dB, coupling loss of 1 kbps, at this rate. So you can see that ECGSM provides a high data rate. The thing is, here it is assumed that 8 PSK with 4 channels are combined. That's why it shows a high data rate. Also, this uses 33 dB. dBm is the transmit power, while NB-IoT uses a 73 dBm. So NB-IoT though uses a less transmit power, 10 dBm less than this, still it gives a much better performance at real far regions, even better than the LTEM, right? So this is about providing the coverage on the cell edges, etc. Second thing is about the latency, right? Though latency is not a critical aspect from a NB-IoT sort of a or cellular IoT perspective, or massive IoT perspective rather, right? But still, this simulation, what is done is that in case if there is a problem on the device edge, the time taken by the device to respond and inform the network about the problems there. Right, so error reporting or the exception reporting. Right, here again you can see that this is the 164 dB. This maximum coupling loss. So this takes around 10 seconds. So even at a extended cell boundary, within 10 seconds, you will be able to send an error report. Right, and coming on to the battery life perspective, you could see that. The industry expectation is that the device should be lasting for say around 10 years. So this simulation uses a 20 byte message for a day, per day, a sort of a situation where the device comes up, sends it to 200 bytes and goes back to sleep. Right. So in this case too, you can see that on the extended cell boundary, still it can give around 10 plus years of battery life, right? So this is just to show that how these technology can work at different the real environments in the cell, near to the cell and the cell boundaries. Because there could be a technology which can give a very good performance at the near to the cell, but cell boundaries, it is a very difficult situation, especially at the interior, inside the buildings, under the ground, etc. Right? So 1 minute. Let's move on. So the next slide is on the feature difference comparison between NB-IoT and EMTC. I'm not getting too much into the ECGSM, which I don't really feel is going to really kick off, because that is not going to be part of 5G. It was something to make the devices which are the GPS devices used for IoT, how to make them cheaper. But then I don't really see a real business case there, and not many people are promoting that much. So I will not go through each of them. So basically, NB-IoT doesn't support voice. and it doesn't support broadcast. In release 14, ACPTM was introduced for mainly from a quota perspective, basically the firmware and the software upgrade of the devices. While EMTC supports all this, because all these are LTE features which are continuing to be in the EMTC. And these are the new features introduced in release 13 for the NB-IoT EMTC and even for ECGSM. Right now, the power save mode, control plane, IoT optimization, user plane. Then RLC does not support your mode. It was again added for a CPTM in release 14. EDI RX was added, and we have seen the duplex part of it. So just wanted to brief through that, run through that. Then, because I'm not, the next slides, I will get into the details of these things. Just a minute, I have one small problem here. Give me a minute, I'll just. The slides are not really moving, so just trying to see how to move the slides. Yeah, I think you can see this now, right? Yeah, so power save mode. In case of power save mode, the device can inform the network saying that I'm going to get into a power save mode where I'm going to sleep, and I will come up only at this time. So the power save mode, the device will be still registered with the network. Network knows that the device is there. Network doesn't remove the device, but still it will not do any actions on this device. It will be only registered with the network. So this power save mode timer could change from few seconds, maybe 2 seconds, to around 413 days. So which means basically a device can sleep for more than a year and again come back, right? So when it sleeps, it will shut down all its starts. It's the RF baseband protocol stack, everything is shut down, and it is waiting for a trigger from the application to wake up, right? So which means basically the power, the battery power is not drained during this time. So this is a feature which is used by all these EMTC and NB-IoT perspective. The second thing is the EDRX. The LTE, there was a concept of the DRX where the discontinuous reception, where the device waits for do not look for the paging messages during the DRX mode, discontinuous reception. So the network tells the device that, okay, this much time I'm not going to page you, so you need not look for a paging. You need not look for this thing. This is the time you should look for a paging. Now that timer was very much extended in case of an IoT, and it is the maximum value of this timer can go up to 175 minutes, right? So the good thing about this is that the transceiver could be turned off during this time. We had earlier seen that NB-IoT is a half duplex system, so which means that that you need to have only one transceiver for transmit and receive, because you don't do both at the same time. Now, even that antenna could be turned off. It can move to idle mode if the timer is very small. Otherwise, it could be turned off. Right? Coverage extension is achieved mainly using the repetitions. So basically, the messages could be repeated many number of times. The uplink messages could be repeated up to say around 128 times, because more repetition, the uplink can consume more power from the device. Downlink could be even 2048, right? So so during these repetitions, doing the repetitions, you can ensure that even the receiver, the device which is receiving that, even if it's able to receive only part, you can combine these repetitions and try to make sense out of it, right? So that's one way of getting the extended coverage there. We have seen these different deployments of standalone, guardband, etc. Yeah, control plane CIOT optimization allows you to send data without establishing any data bearers. So this will be sent as part of the mobility messages as a piggyback. The control message itself will carry, when you try to do a registration, the data is in the log. So which means if the data is small, say something like a 10,000 byte, then 1,000 byte, then you need not establish a data bearer to send this data. You can just send this as part of the signaling. And user plane CIOT optimization for NB-IoT is needed because it doesn't support a handover. So basically, if during that user plane data transfer, the data bear perspective, if there is a link issue, you need to do a reselection. You could, suspend the data transfer and establish a connection, then again resume that. So that is another feature. This is something very important from an operator perspective, because operators are looking at use cases. When they have a lot of use cases where the data, the sensors do not support IP. So you need to send non-IP data, and SEF on the network side should be able to manage this. So this is one of the critical features too, right? And so these are the release 13 features, and in release 14, positioning was added, but I don't really see a real need for this, because I still feel that the GPS, GNSS positioning would be a much better option. That's what most of the device guys are trying to use. NB2 was added for the head data rate. Then we have seen, I will not get into too much of this because lack of time. Release 50 had quite a few interesting features, like, this feature best really allows you to do a cryptography, basically for a security perspective. You don't need a additional security on top of this protocol stack. Then TDD support, wake up signals. So basically, we are talking about the DRX mode, etc., where the transceiver the device has to page, look for the paging for the network, right? Now, in this, with a wake up signal, the network will send a separate RF signal, which is not part of this, as a wake up signal. So the RF will be sleeping. Whenever it gets a wake up signal, it knows that, okay, now I need to turn on the NB-IoT RF, and it will turn it on, and then it looks for a paging. And early data transmission, this is again a beauty feature, where this in the RACH, the first, actually there's only two messages sent from the network for the data transmission. First is the RACH message. You get a message from the network, and the message to the data transmission is completed, and the device goes back. So basically, a lot of signaling avoided. This is a very, saves a lot of battery. Yeah. This is achieved using no anchor carrier perspective, and so I think these are some of the features of NB-IoT, that you could see release on release. So EMTC, I'm not going through this because these are very similar features for EMTC or release on release. And NR Light, I want to spend a few minutes. So this is something which is coming, a new thought process. Hardly the thought started last year, and this is going to be part of the release 17. So basically, we talked about the NB-IoT, EMTC, but then there are a lot of use cases where industrial use cases where you need to have much better latency requirements and the reliability requirements, which NB-IoT and EMTC doesn't offer. But now, if you go to the URLCC EMBB use cases, right, it offers that, but then those devices will be pretty complex and expensive, and it will be eating a lot of battery. So they wanted to have a technology which provides a better reliability, but less data rate, not like EMBB, low latency, but with a lower cost and complexity battery life. So you can take this drone use cases or those sort of things in this case, So this is a pictorial representation where in an industrial scenario, which technologies would be used for which all aspects, like, what sensors, what things will use which technology, right? So I think so this was about the technology. Now quickly I will move on to some of the design and implementation aspects of the protocol stack and the SOC. So this is about the protocol stack perspective. So to look into the protocol stack aspect, we need to understand a bit about NB-IoT 5-layer. I see I have only less than 20 minutes now, so I will try to quickly cover some important aspect. We'll not get into the things during Q&A. If you want to discuss, we can discuss. Basically, we want to say that if you look at the downlink frame structure of NB-IoT, this is exactly same as LTE. Basically, you have a 10 millisecond frame and 1 millisecond subframe with the 2 slots of 5 millisecond. So if you look at the 180 kilohertz with the 15 kilohertz subcarrier, there could be 12 subcarriers there and sort of things. Right now, interesting thing I want to cover was the UL part. In the UL, they have introduced a new numerology of 3.75 kilohertz. Right, so the 3.75 kilohertz is nothing heard in the LTE, right? And so here each frame is divided into 5 slots and each of 2 milliseconds. Now, what the purpose of this maybe is, you can see many faults. One of the main aspect here is in the repetition perspective, right? Now, if the device is very close to the base station, you can go with a multi-tone, which is a 15 kilohertz is called a multi-tone, and 3.75. Sorry, all right, So 15 kilohertz subcarrier or a 3.75 kilohertz subcarrier. In each one, you can have a single carrier, multi-carrier perspective, right? So if the device is very close to the base station, then you can have 15 kilohertz subcarrier. There's no issues because it gives the peak power needed is very less, and you can do the data transmission better. But the point is, if you allocate the complete subcarrier, complete 180 kilohertz to one, device, you are blocking the other devices, right? Especially when you are moving towards the cell edge, you need to do retransmissions. Now, if you do retransmissions across all the carriers, then the other devices will be blocked. So as you move towards the cell boundary, you will be allocated with a 3.75 kilohertz numerology, where you will be using only very small spectrum, and the other spectrum will be available for others. So which channel maps into all these things, maybe we can discuss if you get time at the end. So basically, I wanted to tell the structure of this. And so if you see here, right, you can see that if you take them, okay, before getting into this, the waveform perspective, right? So NB-IoT is a 200 kilohertz waveform. While LTE perspective, if you look at the sampling, is at a much higher rates, right? Because it is the bandwidth is much higher. So it is around 30 Mbps sort of a samples per second sort of things, while here is 1.92 million samples per second. So this, the A to D and D to D conversion of the signals, so that becomes much easier in case of NB-IoT, which gets a simplified RF, which can get the IQ samples much easier and provide, right? That's one part of it. Now, we have seen that if you need only one RF, you don't need a transmit and receive. It could be, it's the same RF could act as TX and RX. Also, like I said earlier, the same RF, if it supports L-band for GPS, it can have a switch whenever the NB-IoT is not using this. The same thing could be used as a GPS transceiver too. So that way, a lot of cost comes down from that perspective. Now, coming on the processing of the signal, you can see that between the DCI to the downlink processing on the device, you get at least a 4 millisecond time, and the ARC-NAT, you need to send the uplink only after 12 milliseconds. So, you can use a very slow processor which can process this sequentially. The same is the case in the uplink too, right? Once you get the uplink grant, you get at least 8 milliseconds to send the data and 3 milliseconds for this thing. So basically, what we are trying to say is that if you receive a message in the RF, it could be processed by the PHY, the layer 2, layer 3, and processed with the application. Then the response goes. So it could be a chain. You need not really have multiple processing systems processing this in parallel, right? So that makes architecture much simpler. Right, you need not have so many threads and sort of things to parallelly run all these things. Maybe some of the aspects here could be some of the algorithms like the Viterbi algorithm, FFT, etc. Could be one of the complicated things here, which if you have a with better accelerators, that can really help here, right? Now, another thing is in case of LTE, if you take, there is a TTA synchronization between the PHY and upper layers to ensure that the data comes onto the PHY and the RF in time, right? But since you have a lot of time here, right, you need not have that sort of synchronization, because that synchronization also takes a lot of CPU time, right? So only thing is the upper layer has to tell them a PHY saying that send this message on this frame number, and you just need to schedule there rather than looking at the display. And coming on to the design, so what we've seen here was more like a physical layer simplification, which helps a simple design of the device. Now, coming on to the binary and memory footprint perspective, all these things really helps you to design a single architecture where you can have maybe on the physical layer, you can have a one thread which will handle maybe the both TX and RX one after the other. Whenever it gets interrupted, it does action based on that. And the same way for the upper layers, there could be a thread for the control plane and the data plane, and some supporting utility thread for the timers, etc. Right? So you can this way you can design a system which is very small footprint, binary size, the memory requirement perspective, and the interaction between the layers, right? So all these things could be taken care, designed completely differently with respect to normal cellular architecture, like LTE or 5G, the eMBB, right? So the point I wanted to make is that NB-IoT EMTC sort of system should be looked completely differently from a normal cellular modem. It should be designed, keeping all this, making use of the technological facilities the technology provide. You need to look at the system architect as per that and take care of it. Like so, like I said earlier, some of the algorithms, the Viterbi and FFT encryption, etc. If the DSP or the MCU supports, it can really reduce the MIPS too, right? So yeah, so these are general implementation guidelines which anybody will take care any modern design perspective. But I just put it here because in other case it's a need, but here in case of NB-IoT and the EMTC, etc., these sort of aspects like zero copy and all the things are mandatory because we can't afford to do this, right? So I think I have hardly 20 minutes, 10 minutes. But maybe in another 5 minutes, I'll try to wind off and try to give another 5 minutes for the Q&A. So next, I have on the SOC perspective, we have seen a protocol, a design perspective, how the technology and what are things we need to take care, right? Now we will see how to look at some of the SOC aspects. Like again, the way we have seen earlier, if you look at the LTE SOC, etc., right? So those they have a lot of components for each and everything. There is a hardware component, there is a chip or a coprocessor or accelerator, right? Because the systems are pretty complicated there, and you need to have parallel processing of all these things, all these components to achieve this. But in case of these technologies, you could use a very low power CPU or a DSP. Only thing is you need to have some few targeted hardware accelerators like encryption for AES encryption is supported. So because you cannot have a separate encryption hardware for AES, because that would be again expensive, unlike LTE, right? The DSP or CPU supports with AB decoding, FFT sort of thing. If they are built into then those CPUs could be, one CPU should be good enough to manage the complete aspects. You don't really need a lot of components there, right? So before we get into the SOC high-level architecture, we'll just look at the power management part of it, right? Because actually so that power management is very critical. So you need to have different power domains for different aspects whenever we talk about the DRX mode or the PSM mode. So each of the mode we should be able to control the processor, the transceiver, baseband, protocol stack, all by we should have the flexibility to control it, so that it can really provide you real benefit of the power management. Right. So as per standard, the PSM definitely the stack everything is shut down and everything go to sleep. But if you look at the EDRX, the duration too, it is around 175. You can go up to minutes, right? So even EDRX can get into the similar mode. Only thing is, whenever you get into this mode, you need to clearly take care of the data retention, ensuring that also relevant data has to be retained in a retention memory or put in a backup memory, flash or something, and put it back whenever you come back. So basically, the upper layers inform the power management when to shut down what all things based on the configuration, and it shut it down based on the power domains. And only exception could be the application processor. If the application wants to send something on priority, it can wake the power management module saying that wake up, I want to send something irrespective of this, right? So just wanted to spare something on that. And this is a quick high level, very high level view of a SOC. It's not a fully, because I don't want to share a real commercial designs here. So basically you can see this is in the simple SOC. You have a MCU and DSP where the critical code segment runs in the instruction memory and critical data resides here. The remaining that can the code could be in the SRAM, the RF and baseband all integrated through some bus, and you have flash and other analog circuitry, power circuitry, and IO, PLL, all other things with it. So basically, if you look at this, you can see that everything should be integrated to a single SOC with a single architecture, so that the overall gate count of the SOC remains pretty low, which really decides the cost of the SOC, right? So now I have one or two more slides. So this is a typical performance numbers of an SOC, like So with what is the memory requirements, right? We have a system where the RAM requirements are less than 512 KB, the binary flash where the binary was stored for all layers, layer 1, layer 2, layer 3, all together, it's less than 1 MB. MIPS actually it's even around 60 MB, but I'm just giving it as 100, right? And you can look at some power consumption numbers, which are beautiful numbers. Like this depends mainly on the platform, the DSPs or the MCUs. Like you can see that 0.5 microamps at during the sleep mode. And as you know, most of the time the devices will be sleeping. So the power consumption of the device is mainly decided by this parameter, not the peak transmit power, because the peak transmit power will be used only once in a while. Most of the time the device is sleeping. So if this is not low, your device is going to really drain the battery, right? So also look at the SOC size. It's only 8 mm by 8 mm, right? So this is a SOC which meets what we are talking about: low battery consumption, low cost of the device because of the sizes, sort of thing, right? I think I have one more slide quickly. Just want to indicate, not talk much about unless somebody asks questions. So this till here, the main part is completed. I covered the technological part, the protocols design part, the SOC part. Now, so we have seen that a lot of people have deployed this, right? Operators. Now, that's, and I mean, it's not that everything is beauty, right? From an operator perspective, they are still facing a lot of challenge, because the cost of the module, though I said that this could be done by this, most of the devices, modules available in the market now are designed by the cellular device companies who are used to making only the LTE sort of broadband chips, and the NB-IoT EMTC SOCs do not follow this sort of an architecture, and hence they are pretty huge. The size, the SOC size, and the the cost of the SOC is very high. It's around $15-20 perspective. Second thing is the battery. It's a lot of battery. Though technology provides you options to do that, we have seen how multiple power domain, etc., should be implemented. But that, I'm not talking about the OS power modes and sort of things. So, in case of an LTE mobile phone perspective, you don't really see this as a main requirement. But then you need, this is very critical, and many of these modules are eating battery like anything when really deployed. And the third thing is, all these devices have to undergo complete certification like any other cellular device, which is very time consuming, and the performance testing, operator testing, a lot of things there, right? Now, finally, the thing is like, the business applications and the ecosystem, right? For the operator perspective, they need to have the use cases, the modules ready, the services ready, right? And all these things should get into a viable business model, and the business has to come, only then the volume will increase, right? So the cost and things will come down as the volume increases. So at the beginning, since we are at the early stage of the technology, the operators are looking at, let's try with some small numbers and see how things work, then I will increase. But then to try with a small number, the SOC module making cost is high. So which makes that, it is not that easy to get to the break-even at the beginning, right? So these are some of the issues faced by the operators, but definitely, the industry will get over this. The cost will come down, but the performance will improve, and the business ecosystem will fall in place. And definitely, there is a great future for this technology. So I would say that that's all. I just have one slide just to show the use case. Here you can see. So here the NVIDIA is sending the data to the network. So this is a demonstration. I've just used a development board, not the customer or the production things here. So here you can see, we have used a smart meter connected to a development board, and using the ADA RF we have sent to the network. And there the automatic meter reading application, it gets this AMR details. You can see the phases, 3 phases of voltage and current, the more details of that, and the billing report, etc. in case of smart meter. Right. So I think I would like to take this stop here, and I hope I covered what I wanted. I'm not sure what I covered, what you were looking for, your expectations. So I'll try to answer a few questions here. If you have more questions, you can reach out to me on this mail ID, and I'll respond back.
Oh, that's really great. Really great. Very great. Thank you very much, Jomi sir, for giving such a large and huge pack of information in a very short period of time, but very well delivered. Very well delivered. Thank you very much. So we have a few questions as well. So let me see. Yeah. So we'll take some questions.
Yes, please.
Yeah, let me just go on to this. Yeah, the question is number 1: will the IP address be maintained by device when device comes out of PSM mode?
Yes. So basically, in the PSM mode, like we have seen, right. I just talked about the data retention, right? So, and not only the IP address, actually the device is still registered with the network. The session is still registered. It's not that session is gone off, though it is more like a session is suspended. So all the NAS state and all the information is retained. So if it is a short time, right, if it is not really a long time, you could put this information in a retention memory, which could be powered still at a lower clock. Or if the duration is more, you could even take a backup of all this into the flash, and whenever the device comes back again, right, this will be put it back onto the device, right? So basically, if this timer is say 1 day, you need some time before that 1 day just for the boot up, etc. So you need to fine tune that PSN timer and tell to the hardware saying that you wake up few little time ahead, so that exactly 1 day I'm up there.
Okay, okay, that's very great. Another is in our Indian scenario, how effectively cellular IoT use case is possible as per standard? Is it customized?
Um, I don't see there is any need for the customization for our scenario, right? Because there's nothing different that we have. Only thing is, it is a question of the business cases, right? So in India, being the price is a concern, right? Unless you do the break even, right? So the business models really will not take off. So initial deployments of this could be on not for the common man. You can have a common use cases like you can have a NB-IoT small tag which you can put in your kid's bag, and where the kid is at any time, right? So that could be a simple use case. But then that sort of use case is not going to happen in India soon. While smart meter could be one of the use case where the electricity board people feel that why I should send a person monthly to take a reading, etc. Right? So for them there is a real benefit coming out of it. So the initial use cases could be enterprise use cases. Later it could be a mass use case. So it will take some time, but then there's no need of any customization. The use cases could be different, because I heard in Europe that one practical use case which made money also, that they said it's making profit for them. It was something like the cattle when they go for grazing, they put this device to track the cattle. But then they say it makes a lot of money out of it, because they know where the cattle is, they can get back in time, and they can get the milk in time. So which is really a business use case. But from Indian context perspective, you may feel like, yeah, right. So I mean,
Okay.
the use cases can use
Yeah,
cases might
yeah,
vary, but then
yeah,
definitely
yeah,
the technology makes sense. Yeah.
yeah, yeah. It is business case that okay, fine. Another question. Although this talk is focused on terrestrial IoT technologies, but I would like to ask, how do you see the prospects of satellite-based IoT in future, especially the LEO satellite?
Yeah,
Just in
actually, the
just continue in that, I believe. Release 15 and 16 have NTN network support as a backhaul. The same is being extended for IoT in release 17. There is an ongoing work item on that. What is your views?
Yeah, actually, it's a beautiful question, I would say, because you look at, say, the agriculture farm sort of use cases where, there could be huge area, where has to be covered. So that could be really far, remote, and huge area. So now, how do you provide a backhaul connectivity, right? So definitely there are many people looking at this NB-IoT sort of a thing, like more like a private deployments in these cases, and connecting this as a backhaul through satellite. Yeah, and especially the good thing in NB-IoT is that anyway it's a slow system. Most of the time when you put a satellite, the problem is the delay part, right? So definitely the technology can take up. So there are already people who are looking at this sort of use cases, and definitely this will come up in the future.
Okay. On slide 30, that is performance footprints, are these numbers maximum or typical? What is the application?
So these are reference values. Okay, these are the typical values, or I would say good values. Okay, so for me this value looks good, right? So this sort of a number can really get me a system SoC with what are our initial requirements, the low cost. The SoC cost is supposed to be less than $2. That is the NB-IoT expectation, and double for MTC, right? So this is for NB-IoT, right? So and the module price, and module includes all the application processes and sensors and sim, all the things together, right? So this is something which can achieve you what are we talking about? Sub $2 cost with a very good battery performance. So this is a reference value what you can take it, and I would say from industry perspective this is one of the best numbers.
Okay, very good. One another question is why do call it as 5G? It is basically LTE and no antenna array, no millimeter wave, very low power and ranges and low bandwidth. So even after this, we call it as a 5G. Why?
Yeah, actually that is a misconception with people, because this one people should really understand. 5G is not 4G plus plus, right? That is see, if you look at the technologies, like I said at the beginning, first two technologies were voice. 3G started with data, what was perfected in 4G. Look at 5G. 5G is not broadband. It's not massive MIMO. 5G doesn't say 5G requirements are from ITU. 5G requirement, any system meeting IMT 2020, this requirements from ITU. ITU says, these are the KPIs, but doesn't say that every use case has to meet every KPI here. It's not that every use case needs a 20 Gbps peak throughput and sort of things, right? So that's why actually you look at they came with a use case scenario saying that this aspect. So if you are going for an NB-IoT, massive machine type communication of this use case, what we are talking about, how can you go? What is the need of a massive MIMO there, right? Massive MIMO you need wherever you need a high data rate and sort of things, right? So all the things, 5G is not a single technology. You need to understand that 5G has to cater for all these things, and one single system can cater all these KPIs together. So if you look at a 5G network perspective, there's a network slicing, catering to different use cases, meeting different things. So that's why I said I put this slide here. In 5G, to meet this, they are defined. They are not defining any new standards. It's NB-IoT and EMTC. I think we are, going with 4G and massive MIMO. That initial hype of 5G, right? It's more, right? 5G has, and I believe it's my personal belief that more money for the operators will come from this part of 5G, not from the broadband.
Yeah,
right?
So let the question who I asked, let him tell as a 4G only, not 5G. Okay. Yeah, good. Okay. So another question is, what could be the maximum distance between energy meter and AMR application server in the slide 35? Whether any license is required for frequency?
No, actually, this is right. Okay, so this is my lab environment I just shown here, right? So basically, you need to look at this. This is the device which is getting connected to the base station and the port network and the cloud and sort of things, right? So basically, the application, the smart meter application, establishes a co-op or MQTT connection over UDP to the core on the cloud, right? So the application is running here. So it doesn't matter where is these things, right? Now, if your question is about how far this UE and the base station is, we are talking about, minimum coupling loss of 165 dB, etc. So the coverage, if you look at Now it is 15 kilometers now with a release 15x, like it's trying to extend for 100 kilometers, like we are talking about the satellite cases, etc. Right? So basically the release as of now it is 15 kilometers, but it could be extended to later 40 and 100 sort of kilometers here. Now, from this slide 35 perspective, this is just a lab. So, actually we have connected this through RF cable. So it's a lab demo. It doesn't matter whether I can put a small antenna here, but they are sitting very close by, because this base station is not a commercial antenna transmitting at the same power as this. Yeah.
Okay, that's fine. Very great. I think one question. So Ganesha sir, you can go ahead, unmute yourself and ask question. Dr. Ganesha sir. Yeah.
Jovi, it's a great talk. I have a very generic question. Among these LPWAN technologies, which one you think it is deployed widely and making money as of now?
Yeah, so again, it's a good question, right? So basically the perspective, if you look at the technological part, right? So LoRa and Sigfox had started off long time back, actually, these two technologies, right? And 2016 is the time when cellular guys realized that, okay, we are left out, we don't have anything and we need to have something, and they came out with this, right? Now, if you look at the telcos perspective, most of them are going with this NB-IoT sort of technologies, while the people who did not have a license spectrum, because this is a license spectrum, so companies like Alibaba, Comcast, etc., they are preferring LoRa. They are going to go in a LoRa way. Sigfox act as an operator. They don't really provide, they install their own network and they provide the services. So I would say that the LoRa is the main one. Sigfox is lower, but these are the technologies which is coming up. But then NB-IoT maybe because of the 5G hype, the broadband hype, so 2018, 2017, 2018 started off, 2019 there was a dip. Now again it should pick off. So basically, I feel like later all will find their own sweet spot, like our 4G and Wi-Fi. LoRa is very well suited for enterprise use cases where if I have an enterprise where I want to deploy my own network, I can do that. While NB-IoT could be more of a public use cases, Sigfox could be used for very specific use cases, which is very cost effective. But the problem is that the capabilities are very limited. So right now, LoRa is one of the dominant player here, while these things are catching up. You can also see that this came much later, right? And these are later technologies. So if you look at the technology perspective, these technologies really started 2010. It's a 10-year-old technology, Sigfox LoRa, while this is a hardly 4-year technology.
Yeah, but the technology like LoRa or Sigfox, does it? Will it scale? Basically, like they say 40,000 devices per gateway. But since it is more like an asynchronous network, will it not? The interference will start killing it, right? So that's
right. That's right. So basically, since it uses the ISM band, it cannot scale into these things. So this uses a spectrum, while this uses a very narrow band. So here, what it does is that band is split into very small things, and so again, though they support 1 million, the catch here is that you can send only 10 Gbps, the frequency is less, and sort of thing. So the use cases where you use these things can use it. So I find that Sigfox, though they had a lot of initial hype, they are struggling. LoRa has found some space in the enterprise perspective within their campus and sort of things. Right. So, but as a public LP1 perspective, definitely, I think NB-IoT should come up. Now, the challenge there is the cost factor, right, and the power consumption of the existing chipsets, like what I was showing the last slide where I was talking about the operator challenges, right? So, once these things are, taken care, I think this will move quite fast quickly.
okay.
Oh, Thank you very much. Thank you. I think that's all. If there is any question still, you can throw us, send us in the email. Speaker, realize me if you wish. So thank you very much to all of you. And Jomi sir, thank you very much. Very nice talk and very huge, large number of information in a very short period of time. Very nice. Thank you very much. So participate.
Thank you all.
Night and come join us again tomorrow. Very interesting talk on Massive MIMO. Tomorrow, same time, 7:30. Thank you very much. Bye.
Thank you. Bye.